welcome to the 45th Porous Media Tea Time Talks. We are part of the Interpol Young Academy. With these webinars, we want to give junior researchers working on porous media a chance to present their work to the scientific community worldwide. This is meant to be a complementary platform to the geoscience and geoenergy webinars, as well as the Interpol annual conference, which will take place in May in Edinburgh this year. I am Mohammadjavad from University of Oslo, and I'm here today with my co-organizers, Sarah Perez from UPPA University in France and Catherine Esprin from Stanford University in USA. Today, first presentation is by Javad Shokri. Javad is a reservoir engineer by background, and he joined the IMPRESS group at the University of Manchester in 2019. Through collaboration with various scientists and researchers, he hopes to reduce global emission while shaping a sustainable future for the energy sector. Today, he is going to talk about porous media microstructures and batteries. Thank you, Javad, for joining us today, and the floor is yours.
Thank you very much, Mohammed, for your nice introduction. I'm Javad Shokri. I'm working as a PhD student at University of Manchester. And what I'm going to talk about today is part of my PhD that we investigated the impact of porous microstructure on the performance of redox flow batteries. This is a modeling study using pore network model, and I would like to thank my colleagues for helping me to do this research. And also this research has been published in the Journal of Electrochemical Society. If you would like to contact us, you can use my email address for the future collaboration. So, okay. As projected by officials, we can say the energy consumption is probably to increase by about 50% until 2050, and in order to in all sectors, and to look at individual source of energy sources, we can see renewable energy sources are growing very fast, and which is a good news for the global warming and global emissions. But the problem for renewable sources is the intermittency and the unpredictability of these sources. To explain a bit more about the unpredictability of renewables, if we imagine we have a solar and wind farm here, which is producing enough energy for the consumers in a city. In the peak hour, in the time that we have a lot of these solar and wind energy, we can send the excess power to some batteries. In this case, we are using RFBs, redox flow batteries, to store the excess amount of energy in this kind of batteries. And whenever the supply, for example, during nighttime, when the solar energy is not there, or whenever the wind is not enough, we can use RFPs, integrate RFPs into the grid and stabilize and the supply rate to the consumers in a city. So this is the importance of the research that we carried out. And in RFPs, there are a lot of different parameters that can be altered to increase the performance. But one of the most important things that we focused on as we are working on porous medium is the electrode of the battery. In the commercial sense, usually electrodes are made of carbon papers, cloth, and felts. The thing is, these materials are not specifically designed for redox flow batteries, so the microstructure sometimes need a bit of improvement to be suitable for our purposes. One of the promising methods to improve the microstructure is to use ordered microstructures, as for example Daniel Niblet used in one of the fuel cells. it was able to improve the conductivity of electrons and also improve the flow of one-phase and two-phase flow. So in this work, we used the same kind of structure for which is 3D printable actually, using 3D printing methods, and investigated the experimental data, and also we compared it to an equivalent ordered microstructure. Then we conducted a parametric study on the ordered microstructure properties to identify the critical parameters controlling flow condition and performance of the battery. And at the end, we came up with an improved microstructure for the flow-through and interdigitated flow field. To touch upon the methodology, I should say we use hydrogen bromine redox flow battery, which we focused on the cathode side during the discharge process. During the discharge process, we have this reaction that bromine is reduced to bromide, and also we used pore network modeling to simulate the single phase Newtonian incompressible and steady state flow. And also these equations can represent the pressure distribution, charge distribution, and species distribution in the cathode side of the hydrogen bromide redox flow battery. We focused on two flow fields. One of them flows through flow field, and the other one is interdigitated flow field. And the boundary condition is constant pressure for the inlet and the outlet, and also next to current collector and the membrane, we have no slip flow boundary condition, and also you can see other boundary conditions for the concentration and also for the flow field. So here, this is the first part of the results. On the figure A, this is the carbon paper, which is commercially available. We used this carbon paper and extracted the unstructured network that you can see we presented here using balls and so the black color shows the carbon paper, and also other colors show the pore network extracted from the carbon paper using Aviso software. So the importance here is we were looking, we wanted to investigate how can we improve the performance of the redox flow battery using a cubic lattice with the same permeability and flow rate. So what we have done is we extracted the network, we ran the simulation, and you can see the results of the unstructured network here in the green, in the yellow, in the orange color. And also we constructed another network which represents the cubic lattice with the same permeability and microstructure properties such as porosity. And we ran another simulation, and the blue plot is the result of the ordered microstructure. So to explain a bit more why we see a difference, I can say the homogeneous and non-tortuous microstructure of the cubic lattice actually is enhancing the convective, the advective flow, and also the diffusive flow in the through plane and in plane direction in the cathode side. And because of that, we can observe an improved performance of the battery, which is about 30% higher than the carbon paper. Also, these two figures show that this is for the unstructured network or the carbon paper, and this is for the cubic lattice. As you can see, the non-homogeneous or heterogeneous nature of the carbon paper imposes some micro starvation in the carbon paper, which is detrimental to the performance of the battery. But here, as you can see, because it's very homogeneous and well structured, everything is consumed properly without having a local starvation. The other parameter we investigated is so for example, now we realized having an ordered microstructure would be better for the performance. So if we are going to print a structured porous medium, what should be for example, the pore to throat size ratio, or what would be the size of the lattice unit? The reason this was the motivation for this part of the research. In the flow through flow field, we constructed 6 networks, as you can see, from FT1 to FT6. And from FT1 to FT4, we have different sizes, different ratios for the pore to throat size. And also from FT4 to FT6, we kept the throat length constant, but we changed the uh, surface area. So here also we kept the permeability constant for all networks, because as long as you're not changing the permeability, the advection force is constant, so we can compare the results under the same advective condition. We kept the permeability constant, we kept the flow rate constant, and the results show an improvement for the networks who that has a higher specific surface area and also a smaller lattice unit. In this part, the only factor which is playing a role is the specific surface area, that obviously by increasing the specific surface area, the performance of the battery was improving. And at the end of this part, we, based on the results from the previous sections, we decided to have this structure for the flow through and this microstructure for the interdigitated flow field. So to explain a bit more about this, we divided the electrode to 2 parts, block 1 and block 2. Block 1 has a higher permeability compared to the block 2, which you can see the permeability contrast between block 1 and 2 here. The reason behind it is, as you can see in this figure, for example, this part is closer to the membrane and this part is closer to the current collector. During the discharge process, we can see all the species are consumed closer to the membrane, and less consumption or less reaction is occurring close to the current collector. Because of that, we thought if we can divert the flow direction toward the membrane and supply more reactants closer to the membrane, it would be beneficial to the performance of the battery. So in this case, we came up with this configuration, and in the interdigitated flow field, we came up with this configuration. And as you can see, for example, for FD14, which is this figure, and FD15, which is this figure, we have a higher performance at the same operational condition. And the reason behind that is, as I said before, we are diverting the flow path of reactants more toward the membrane, which more reaction is occurring, and this is basically helping the battery to work better and produce more electricity at the same flow and operational condition. So to conclude, from the first part of the study, we realized that an ordered microstructure can improve up to 35% compared to the carbon paper or unstructured network. And the reason behind that is a higher advection and diffusion and lower tortuosity of the ordered lattice. And also from the second part, we found that a bigger pores and a smaller throats and a higher frequency of lattice units resulted in a higher specific surface area and a better performance for the battery. And also at the end, we found that at the constant specific surface area, permeability and flow rate, we could have a better performance in the case of improved microstructure in both flow fields. And the reason behind that was diverting the electrolyte main flow path toward the proximity of the membrane, which more reactions were taking place. Thank you very much for your attention.
Okay, thank you, Javad, for your presentation. It was really interesting, really a challenging application also, about to store the energy and provide resources, renewable resources all the time. So first of all, I would like to encourage the audience to ask questions in the stream. And I will start with one of my own. When you were talking about carbon paper and saying that there are improvements in the performances by using structure meshes, structure pros. Did you manage to see the difference of tortuosity between your carbon paper and your structure really component at the end? What are the changes in tortuosity?
So I actually didn't measure the tortuosity, the actual tortuosity in the carbon paper,
So
but
how do you came up with the conclusion of
sorry?
there is a so how do you come up with the conclusion that there is a really difference of
Yeah,
tortuosity
yeah, I was
between
saying.
those?
So I didn't measure the actual tortuosity in this structure, but here you can see all the connections are straight, right? So um, uh, implicitly we can say the tortuosity here is very low, especially in the through plane, in the flow through flow field. But one of the measures for the tortuosity that we used was the number of connectivities of each pore in the uh, carbon paper and the cubic glasses, right? So in the carbon paper, every pore was connected to about 12 yes, about 12 pores, and that's basically making it a bit more tortuous. But
Okay.
obviously, that's a good suggestion to measure the tortuosity using different method like image analysis or anything else.
Yeah, but I'm curious about the ratio, the different ratio between both of them.
Yeah,
And yeah, and so this improves the conductivity, right?
improves the connectivity between pores.
And then but you are talking about performances, battery performances, but for me it's not clear what we can improve. So could you specify a bit more, please?
Specify about what? I'm not. I'm trying to understand the question a bit better. Can you explain a bit further?
I mean, in reducing the tortuosity, for instance, here, how do it impact the performance of the battery and which one? Because you
But
can improve the storage, you can improve the conductivity, you can improve several things.
okay, so here is improving the diffusion first of all, because uh, so we have three forces in the battery in this simulation. One of them is advection, the other one is diffusion and migration. Uh, the tortuosity is directly affecting all of this, but because we kept the flow condition constant in both networks, we cannot say advection is improved, right? But we can say diffusion and migration are improved,
Okay.
right? And that's because you have a straight flow path for the species to go toward the reaction sites. So it's affecting the diffusivity and sorry, it's affecting the diffusion and migration forces.
Okay. Okay. Thank you. Thank you. Any question from the studio there?
Yeah, I have a question. So Javad, I really liked your talk. On like one of your final slides where you showed the two different kind of setups.
Okay, that's
You
my
had
fault.
two different setups, and you had like one that had better current density than the other. And I was just wondering, have you tried like running like an optimization tool where it tries like many different setups and to see just basically if the best optimal setup is something simple or if it produces something crazy?
Yeah, I get your point. That's a very interesting question actually, because especially recently people have started using like different uh, machine learning methods and optimization methods. No, we haven't done it, but I am aware that there are another group in Eindhoven recently published some works on this matter that you mentioned. So if you're interested to know more about that, I can send you those papers which use machine learning methods.
Okay. Thank you. I think Mohammed, see if you have a question. Otherwise, I don't see anyone in the chat. So if you want to get in touch with Javad, then ask question afterwards. Please feel free to contact him. And I will thank you again for your presentation. And
Thank you very much, all of you.
okay, and we will move to the next speaker of the day. So our second speaker is André Matias. He is a final year PhD student at the University of Lisbon. He is studying the flow through time involving porous media. And besides its PhD endeavor, he still works with granular system applied to biological system and food pores, because during his master he studied the electrostatical of granular matters and its relevance in planet formation. And today he is going to present his work on swelling, erosion, and dissolution in porous media, and we will learn how to make the perfect coffee. So then, André, the floor is yours.
Okay, so thank you very much and good afternoon to everyone in the audience. So as Sarah said, I'm André Matias and I'm on the final stages of my PhD. And this presentation will be roughly a summary of most of the work that I've been done in my PhD regarding the flow through porous media. And I always try to motivate my work on how to make the perfect coffee. And to make the perfect coffee, most of us know that we need to balance carefully several ingredients like the quantity of water, the temperature of the water, the pressure of the water, and finally the blend of the coffee. And all of these factors will impact the coffee that we drink. But when we are preparing the coffee, often we disregard a lot of interesting physical mechanisms that happen. So, for example, the coffee grains absorb water, and during the absorption, they swell. At the same time, as the water flows to the grains, there is erosion due to the shear stress that the water causes on the surface of the grains. Also, there is dissolution of chemical compounds, such as the caffeine that we all look for in the coffee. And finally, as the water flows, there is the movement of some small particles that can lead to the blockage of filters or can lead to the transport of fines up to the coffee cup. And although I motivate my work using coffee, we can find all of these things throughout nature, such as, for example, the swelling of clay materials that is present in the ground, the erosion of the sandstone present when we are extracting oil, or the evaporation and drying of grains in silos. And finally, the movement of solid can be one of the factors that lead to kidney failure and the kidney stones. So on this presentation, I will start by focusing on the swelling and erosion. And regarding these two mechanisms, they can be described as follows. Regarding the erosion, as the fluid flows past the grains, there is shear stresses that are represented here by this TW that arise. And if the shear stress is large enough, then some amount of mass is ripped off from the grain and is then transported by the fluid flow. For the mass to be removed from the grain, the shear stress needs to be above a given erosion threshold. And so we have a local thing. So the shear stress locally will rip off part of the grain and then transport it across with the fluid flow. On the other hand, we have swelling. And as I said before, the swelling happens due to the diffusion of water inside of the grains. And as the water diffuses inside of the grains, we can observe and measure experimentally that the volume of the grains will increase exponentially in time. And the how fast the volume will increase will depend on a given time scale. On this side, the swelling, it's something that happens globally to the grains, and we need to somehow see what happens to the locally. And as you'll see afterwards, I do numerical works, and it was a key thing in my work to balance between having a local behavior like the erosion and having something global of the grain and try to implement it. For you to remember later, I put here some key remarks, such as that the amount of mass that we remove will be proportional to the shear stress, and it depends on the erosion threshold, and the volume of the grains increases exponentially in time with a particular swelling time scale. So when we look at the erosion, which is something that depends on the fluid flow, we can see with the Hagen-Poiseuille flow that the shear stress will be more or less proportional to the size of the pores. So if the pores are larger or smaller, the shear stress will be different. And the way the shear stress depends on the pore size will depend if it is a pressure drop that we are imposing as a boundary condition, or if it is a constant flow rate. When we are imposing a pressure drop, the shear stress increases with the pore size. When we are imposing a constant flow rate, then it's the reverse. The shear stress decreases with the pore size. With this in mind, let's see how it is the fluid flow across a porous structure like this one. Starting with a constant pressure drop, we can see that as the time evolves, the grains start to swell, and eventually erosion starts to dominate the dynamics, and the grains start to decrease up to the minimum size that I set. We can more systematically study this by plotting the porosity as function of time. And as if I have a very small erosion threshold, then the porosity will just increase up to the maximum porosity due to erosion. If the erosion threshold is very large, then no erosion happens because the shear stress is always below the erosion threshold, and so the porosity decreases up to the minimum value corresponding to the maximum swelled particles. For intermediate values of the erosion threshold, we arrive to a different values of porosity. This can be summarized by plotting the amount of mass that we remove as function of the erosion threshold. Once again, if I have a very small erosion threshold, then we remove all of the mass. If I have a very large erosion threshold, I remove none of the mass. And in between, we have a sharp transition. And this sharp transition will depend on the swelling time scale, which is the different colors and markers. As we increase the swelling time scale, it takes longer and longer for the particles to swell, meaning that we can erode completely the system with a larger erosion threshold. This sharp transition arises because of this dependence on the shear stress. So as the particles erode, the shear stress gets higher, and so we have a positive feedback driving erosion. The same thing is not true when we have a constant flow rate. So when we have a constant flow rate, as the particles erode, the shear stress decreases. And this means that when we plot the amount of mass that we eroded as function of the erosion threshold, we not only don't see a sharp transition, we see some gradual transition between completely erosion and no erosion. And not only that, it does not depend on the swelling timescale. So this was about the evolution of the pore structure as the fluid flows, but where is the caffeine? One of the most important ingredients in the coffee that we drink. To do so, I implemented also this solution into my model. To include this solution in my model, I need not only to work with the Navier-Stokes equation, but I also need to work with the Advection diffusion equation. And with the Advection diffusion equation, I also need somehow a way to increase the amount of solute that is present in the liquid with the source term. And in this solution, this source term will appear due to the concentration gradient across the boundary of the particles. I want to propose a continuum equation where I describe a set of grains instead of 20 or tens or hundreds grains like I showed on the simulations before. So I propose a continuum equation where instead of considering the velocity at the pore scale, I consider an average velocity, an effective diffusion, and a source term that will be given as such. The source term was determined using the mass transfer rate equation, where we determine the amount of mass that varies due to the dissolution will be proportional to this mass transfer rate. And so the source term will be given like this. With the proposed continuum equation, we can compare how does this equation holds up against an experimental measurement of the caffeine present in a coffee extracted from off the shelf coffee machine. So the black dots will correspond to the experimental measurements of the caffeine concentration as function of the extracted volume. And as we extract more and more coffee, the concentration at the vials decreases, as expected, since the grains will be emptied out of caffeine. The blue line will be the numerical solution of this equation, where we use the mass transfer rate as a fitting parameter to the data, and we see a very good fit. To grasp a little bit more about the dynamics of this continuum equation that we propose, we simulated the same problem of this solution, but this time using pore scale simulations. Since like this, we can compare directly our equation with the mechanics that we are imposing or that we extrapolate from the dissolution. We can measure the concentration content at several spots in space, and when we measure the concentration as function of time, we obtain something like this for the different measuring points. So the points will correspond to the results obtained of the pore scale simulations, and the lines will correspond to the numerical solution of the continuum equation. And we see a very good agreement where, as time moves on, the concentration increases up to a maximum, and then it starts to decrease. The value of the maximum is higher the further down we measure in the system. With the concentration, we can also measure the amount of mass that we are extracting, and we get a similar behavior, that it increases up to a maximum value, and then it stabilizes, and the maximum value is higher for longer domains. With these two quantities, we can make a very similar plot to the experimental measurement of the caffeine content or the solute concentration as function of the extracted volume. We obtain a very similar behavior, and once again, the agreement between the pore scale simulations and the continuum equation are very good. Finally, if we take the continuum equation and go to the limit of very small mass transfer rate, we can simplify the equation by assuming that it is on the steady state. And when it is on the steady state, then the dissolution or the mass transport will be controlled solely by two parameters, the Peclet number and the Sherwood number. And the Peclet number relates the advection with the diffusion, and the Sherwood number, the mass transfer with the diffusion. Here we plot the concentration measured at the outlet of the domain as function of the Peclet number for different densities of particles, and the lines correspond to the analytical solution of the simplified equation for the regime of very small Peclet and the regime of very large Peclet. Once again, we see a very good agreement. And this leads to the end of my presentation, where I showed that I studied the impact of erosion, swelling, and dissolution in the caffeine extraction. We started by making some study about the evolution of the pore structure, and we found that by controlling the fluid flow, we can control how much matter we erode from the pore structure. And we later developed a continuum model to describe the dissolution that was validated using experimental measurements and pore scale simulations. Just a side note, here are the details of the social network of my research center, where you can find all the events that we have, and we are always looking for an interested PhD or postdoc researcher. Thank you very much.
Thank you for your talk, André. That was very interesting. Again, like if the audience have any questions, you can like type them in the comments and then I can read them out. But I'll start with a question of my own. I think my most important question, André, is 8 a.m. here in California for me right now. What can I do today to improve my coffee?
So to improve your coffee, if you want the maximum caffeine, you need to decrease the velocity of the extraction. But that has the side effect that you cannot wait infinite time for your coffee. So there is a balance in that.
So there's a trade-off for how slowly the coffee comes out and then gets cold versus the maximum caffeine I can get from it.
Exactly. An easier thing that you can do is that you can grind more your coffee beans such that your specific surface area increases. Mm-hmm. Because I glossed over a bit, but on the proposed equation, this mass transfer rate is hidden inside here the specific surface area. And if you increase the specific surface area, the mass transfer rate will increase.
Mm-hmm. And for both those things, like, is there a trade-off where, like, if you keep increasing the specific surface area, at some point it's going to be too small and then the dissolution is too much? Or is it just like a constant increase?
If the dissolution is too much, then it's something that I don't study a lot, but it's tricky because you are not dissolving solely caffeine. You are dissolving other stuff. And if you grind too much, you dissolve other stuff and you might change the taste of the coffee a little bit.
Mm-hmm. So then that makes your science a little bit harder when taste comes into it. It's harder to quantify the best coffee.
Exactly.
Do I have any questions from the studio?
Yes, I would like to ask a question about the continuum equation for the dissolution. Mm-hmm. Here in your system, you have hot water and you have coffee grains. How can we use the same kind of thinking to use it for CO2 acidified brine or some sort of weak acid when we are dissolving carbonate minerals?
Yes, the equation can be adapted to that. I would imagine that you just need to tweak the mass transfer rate, or maybe this is the first order approximation where we are assuming that the dissolution depends solely on the concentration gradient. But if your dissolution is more delicate, you might tweak the equation and find suitable results.
Do you think is it possible to introduce some limitations for the buffering effect or some sort of surface heterogeneities or things like that?
Yes. First of all, what do you mean buffering effect?
For example, when you are injecting some weak acid, you are able to dissolve your mineral or dissolve your grain until certain point. When you reach the neutral point, then you will stop dissolving your solid. And when we want to study subsurface CO2 storage, we have to take into account the buffering effect.
Yes, I think you can account for that. On this equation, there is these two sets of equations. So there is this one for the solid concentration on the liquid, but I hided it. But the concentration on the surface of the grains also changes in time, because it's limited. So you can put the buffering effect on the concentration on the concentration of the particles, and regarding the heterogeneities, all of that is included inside of the effective diffusion. So I assume that the heterogeneities in the porous structure affect solely how well or not the mixing of the solid happens.
Yeah, okay, great.
I also have a question on this slide, actually. You mentioned during your presentation, and also when you were referring to the acid-carbon transposition, that your mass transfer rate is a fitting parameter.
Mm-hmm.
So my question is, do you set it prior to your simulation, or do you infer it from your experimental data?
So the mass transfer rate was assumed to be a fitting parameter for two reasons. First of all, there is not a lot of information on in the literature about the mass transfer rate specific for caffeine or for organic molecules. And second of all, we didn't measure what is the specific surface area of the coffee beans that we were using. And so we could not know exactly what would be the mass transfer rate of our specific system. So we use it as a fitting parameter, and we search around values that were found for similar materials in the literature.
Okay. So you are fitting it at the same time with your simulation, or prior to your simulation?
So we extracted, we have the data, and then we tweak the parameters such that it fits the data.
Okay, great, thanks.
But regarding that question, that on this result, that is the only fitting parameter. So, for example, the effective diffusion, we left it as such, and in contrast, when we have the pore scale simulations, since we are imposing directly and we know what is the specific surface area, instead of fitting the mass transfer rate, we fitted the diffusion, the effective diffusion coefficient, because it's something that is also tricky to measure because it depends on the velocity.
Okay, thank you very much.
Great. If we have no more questions, I'd like to thank André again for a great talk, and I'd like to thank our other speaker, Javad, for a very interesting talk. So our next Porous Media Tea Time talk is on the 11th of April at 6 p.m. Central European Summertime. We've got two great talks. The first one's on geoelectrical monitoring of calcite dissolution on microfluidic chips. And the second talk will be the role of root hairs on root water uptake, insights from an image-based 3D model. So yeah, make sure you subscribe to our channel and click the reminders so you know when this next talk will be. And then the other thing that I would to say before we finish today is that we have a few new members. So our team is ever growing, and if you are ever interested in joining the team, please send us an email. And so we have two new members. You can see in the bottom left, Ramin and Chiara. So they will be joining us in the coming weeks. So with that, I would like to say thank you for joining today, and we will see you next time.